All right. Good morning, colleagues, and good morning to the learners and everybody who will be watching this video. My name is Amanda Stirman. I am the departmental head for sciences at Hudisa Technical Secondary School. And today I am going to be presenting for you on a topic, electrodynamics. This is a continuation from the presentation which was done by our subject advisor, Mrs. Malahlela. So she already dealt with all the concepts that you need to know and went through the exam guideline. So today my focus is going to be on the application of that content. That means we will just be looking at previous year's question papers to just try and make a link between what she discussed and how to apply it in the exam. Then before we go to the question, I have just a few things that I want us to place our focus on. Firstly, when we deal with this topic of electrodynamics, it's basically dealing with motion of electrons due to a production of an EMF in a conductor. Now, as a learner, when you approach the exam, first of all, you must know the type of machines that are involved, which is your generator and your motor, and then you need to know the principles upon which those two machines operate on, and also the energy conversion in each machine. Then for your generator, you must know that you are having the AC and a DC generator, and you must know the different parts of the generator and the different parts of the motor. And if in a question you are given the picture, you must know how to differentiate, for example, an AC generator from the DC generator, and also a generator from a motor. And then you must also know how to determine the direction of current flow in the generator or in the motor. You also need to know how to draw the graphs that are related with each generator, whether it's AC or DC. Then you also need to know how to calculate your voltages, RMS voltage or maximum voltage, your current, RMS current and maximum current, your resistance and power. So that is basically it. Now, this is one of the topics that is very interesting, but it's not, it's one of those that you need to visualize it to understand it better. So I have found this video on YouTube, which I think will help us to understand better. If you look here, basically this is dealing with electromagnetic induction, which is production of an EMF so that you can have current in your conductor. So as we all know that a magnet, it has a magnetic field around it, and then in this conductor you are having charges, but because there is no EMF that is pushing those charges, they are not moving, hence you are not having a current. And also if you look here on your galvanometer, it's reading 0. So in order for current to start flowing, there must be relative motion between your coil and your magnetic field. So if I push play when the magnet is moving, you can see that there is an EMF that is induced in the coil. Hence, you start to have the flow of electricity or current in there. And so basically, this principle of electromagnetic induction is the principle on which your generators work on. So there must be relative motion between your magnetic field and the coil. Then you will have an EMF that is induced in the coil. Now, when we look at our magnet, the magnet, each magnet is having two poles on it, the north pole and the south pole. And then when the two opposite poles of the magnet are facing each other, then you are going to have a magnetic field or magnetic flux, and it is always flowing from the north pole to the south pole. And then if you place a coil in between those magnets and you move that coil like I showed in the previous section, then that relative motion between the magnetic field and the coil is what is going to produce the EMF, and hence you will also have the current. Now, if we look at the different components of the this one is the different components we are having here in a generator. You'll see that since in a generator the energy conversion is that of mechanical energy to electrical energy, this coil must be mechanically moved. In other words, you must move the coil in this magnetic field so that you can start to have an EMF. So this is a shaft that you use to rotate the coil. And then here you are having the coil itself with also conducting wires. And then these conducting wires, each one of them is attached to two slip rings. Each end of the coil is attached to a slip rings. So when you see these two rings like this, then you must know that the type of a generator that you are having is an AC generator. Then with each slip ring you are having the carbon brushes, which are there to ensure electrical conductivity between what I would call maybe the internal circuit and the external circuit. It's just to ensure that whatever current that is produced in this coil is able to flow to the external circuit. If you look closely here, you can see that this end of the coil is attached to this slip ring and this other end is attached to this slip ring. Then you are having your carbon brushes. Now, when you are looking at this, what is important is for you to know at which positions of the coil do you have an EMF being produced. So for that, I want us to look here. If we look here, I will try to, not use too much English to simplify this. I want us to focus on two positions that this coil will be in, but as it is rotating, it will be in different position. The coil can either be in this vertical position or it can be in a horizontal position. So to simplify this is that when you are having your coil in a vertical position, you will not have EMF being produced. But when you are having your coil in the horizontal position, you will have an EMF that is produced. So if we have to link that to a graph, I would say that if you are having your graph of voltage or EMF versus time, and you have 0 here and we are working with an AC generator. Therefore, this position, when your coil is in this position, in the vertical position, then you are having your graph, your voltage at 0. Your voltage is 0. So whenever, I'm just going to draw maybe one cycle. Whenever the coil is in a vertical position, then the EMF in that conductor is 0. So you will also not have any current. In other words, if you were to attach your galvanometer there, the reading on the galvanometer would be 0 because the coil is in the vertical position. Then if the coil, also I think I have another one. If we look at this question, then that means if we look here, in A and in C, the coil is in a vertical position. Therefore, there is 0 EMF that is produced there because the rate of the change of the magnetic flux in the coil is 0. Then the second position that I want us to focus on is the position whereby your coil is in a horizontal position. When the coil is in the horizontal position, then you are going to have your maximum voltage being produced. So in this position, I'm just going to try to get my video to be in that position. But I think even though here it's not really in a horizontal position, but you get the idea that when the coil is in the is going towards being in a horizontal position, then you start to get a reading on your galvanometer, which is an indication that there is an EMF that is being produced here. I think I got it now. So if your coil is in the horizontal position, you can see when we look here, these light blue lines are indicating the flux lines, that is your magnetic flux. So when this coil is cutting on your magnetic field or your flux line, then you start to get a reading on your galvanometer, which means that there is an EMF that is being produced, and then there will also be current that is flowing. So those will be the position that will correspond with your maximum points. So the type of graph that you are going to get will be a sine graph. It's a sine graph. So it's very important that we are able to relate the position of the position in which our coil is in with the points on the graph. So if we are looking at this point, that means the coil is in a horizontal position. Then you get a maximum value. Also, the same would apply here. It's just that it will be in the opposite direction. Then at this point, when the EMF is reading 0, then what you must know is that the coil is in a vertical position. The coil is in a vertical position. In grade 11, you would have also learned that if the coil is in a, if this coil is in a horizontal position, then the normal of the coil makes an angle of 90 degrees with the flux lines. But when it is in the vertical, when the coil is in the vertical position, then the normal of the coil makes an angle of 0 degrees, because it will be parallel to the flux line. So basically what I wanted to show you here and what I wanted you to remember is that when the coil is in a horizontal position, I keep repeating this so many times because it's important. When this coil is in a horizontal position, you get an EMF. When it is in a, let me see if I can, yes. When it's in a vertical position, then you will not get an EMF. And that will correspond, vertical position correspond with your all the 0 points, including this one. So whenever the value is 0, you have a vertical position for your coil, and whenever the value is maximum, that means the coil is in a horizontal position. And then now the next thing is, now this one is an AC generator. So if we want to have our current, I hope it, I just want to see if we get something where, again, this is, so I think I have nicely found a link here. So these 0 points, they are corresponding to the vertical position of the coil, and then the horizontal points are corresponding to the maximum induced EMF. Now, if you are having an AC generator, but you want to have your current be flowing in one direction, then what you do is you exchange these slip rings and you replace them with a split ring commutator. You swap them with a split ring. I just don't have, let me see if I can get a picture of a, here. Then the slip rings, you can change them, and when you see 2 half rings, we call them the split rings, then you must know that now you are no longer having the AC generator, but you are having a DC generator. And then if it is DC, again, your graph of time versus voltage or induced EMF, this is 0. So your graph, your 0 points, again, they correspond with the position of the graph when it is in a vertical position, and then the difference now is that your graph will look like this. And again, this one is the horizontal position, and here you are having your coil in a vertical position. Then our appliances, they use direct current. That means if you are providing alternating current, then the amount of heat which is generated by the AC generator is not going to be equal throughout. So you need to provide DC current. So we then now talk about the root mean square potential difference, or root mean square current. This is just to say when we are having a root mean square, or VRMS voltage, that is the DC voltage which dissipates, or which is producing the same amount of is the AC potential difference, which is giving the same amount of energy that would be equivalent to the DC potential difference. And I think we know the formulas which are associated with that. So with that background given, I am going to start with this question. When we are looking at this question, it's question 10. I'm just going to use the same questions that are on your terms and definitions. I know that there is a possibility that these questions have been exhausted in schools, but either way, I don't see the harm that could be caused if we repeat those questions in order to emphasize certain points. Now, if we are looking at this question as question 10, it says the diagram shows different positions A, B, C, D, A of the coil in a DC generator for a complete revolution. Now, the coil is rotated clockwise at a constant speed in a uniform magnetic field. The direction of the magnetic field is shown in the diagram. Now, the key words here that we have to look at is that, number one, you are having a generator. That is the first thing. So when you are having a generator, it's important to know what is the energy conversion in a generator. Even before you look at the questions that will be asked, I believe that it is important to analyze your statement, because if you can analyze that statement correctly, you'll find that you have come up with the answers even before you look at the questions. So if you are having a generator, the first thing, what is the energy conversion? It is from mechanical energy to electrical energy. That is the first conversion. Then the second thing is this one. The type of generator. The type of generator. Now, either you are going to have an AC or you are going to have a DC. How do you know if it's AC? You will have the slip rings. This is just your analysis or your data or given information. If it's a DC, you're going to have the split rings. Then the principle on which this generator works on, it uses electromagnetic induction. Yeah? And then the law or the physics law that we use is Faraday's law. Then the last one, to determine the direction of the current, you are going to use the right hand rule. And with the right hand rule, I think you have been taught that you basically use these fingers. This will be the direction of the force. This will be the direction of the magnetic field. And this one will be the direction of the current. So if you are having, let us say, two magnets, so this finger must point from the north to the south. And this one, depending on whether the coil is rotating clockwise or anti-clockwise. Let us see if we can't go back. Let's see here. If we look at this video, it is rotating clockwise. So when you are determining the direction of the current, you will have your, if you're looking at your magnets, that means you will have your this finger pointing in the direction of the field, and it's rotating clockwise. So your thumb, if we are looking on the AB, let me just play it again. If we are looking at the side of AB, if we are looking at AB here, because it's rotating clockwise, that means the thumb will be facing upwards, and then this finger is pointing in the direction of the field. Therefore, automatically this finger is pointing away from your body, which is indicating that the current is flowing from A to B. And then if you go to this side, CD, then again still the field, your finger is pointing the direction of the field, but because of that clockwise rotation, the force now is downwards. So my thumb, you can see, is pointing downwards, and then this middle finger is now pointing in the direction of current. And then if we relate that to the video, that means on this side the current is going from C to D. And I just want to play this again. Okay, I don't think it's necessary. Let me just go back to this question. So you've done your interpretation of the question. Then the other thing that you must do, looking at the position in which our coil is starting, then we can say, okay, position A is in a vertical position. So that means at all these points where my coil is in a vertical position, that will correspond with the point on the graph where it is intercepting the x-axis or the time axis. And this will be this point, and this point. So here you are having A is corresponding with this point. Let's go back again. C is corresponding with this point. And then let's go back again. A, the other last A, is corresponding with this point. And then the second part, position B and D, will be corresponding with your turning points. Will correspond with your turning points. So this is position B and this is position D. Now with this, you have done your data or your given information analysis. Now you can now confidently go to the questions and you see. The first question, it says here, write down the energy conversion that takes place during the operation of a DC generator. You are given there, you are working with DC generator. It says DC, DC, DC. That means if it's DC, therefore this is the graph that I'm working with. It's DC. So let me just again, that would be my A, my B, my C, my D, and my A again. Because the question says DC generator. That means these are my corresponding positions. So the conversion there is from mechanical energy to electrical energy. That is the energy conversion that you are having there. So for 10.1, we are having mechanical energy to electrical energy. And then the second question says, sketch a graph to show how the induced EMF of the generator varies with time. Clearly indicate position A, B, C, D, and A on the graph. Like I said, if you interpret your question well, then you will not struggle. In our interpretation, we said the question is telling us that this is a DC generator, so that we know that our graph is going to be on this positive end only. And then we have our points A, B, C, D, and A. And it's very important that when you draw a graph, you must label your axis. So you've got our graph, voltage, or you can even write the induced EMF versus time. And because our question is showing us that the starting position of this coil is the vertical position, Therefore, our graph will start at 0. But if, for example, the starting position, let's say if this was the starting position, then that means our graph would start at the maximum position. It will start at Vmax. Good. We'll come to the calculations. I just want us to focus on these, questions application. We'll come to the calculations. Let's look at question 12. If we are looking at question 12, it says here, the diagram is a simplified representation of a DC motor. The simplified presentation of a DC motor, the current in the coil is in the XY direction. Now, remember, a motor uses the principle, the motor effect. Let's see. If it is a motor, I say here it's a motor. So again, the DC motor. You are now doing your interpretation. Principle, motor effect. All right. Secondly, to determine direction of current, you are now going to use your left hand rule. If you can learn to do this, I promise you, then you will not struggle at all. And then the energy conversion, electrical to mechanical. Let's see what is the other thing that was given in the statement. Then if you are looking at the diagram here, you can see that you are having split rings. You are having split rings. Let's say we were not told that this is a motor. We're just given this diagram. How would you be able to differentiate the motor from the generator? If you are looking here, for a motor, you must have a source of energy, because you want to take that electrical energy and make mechanical energy. So if it's a motor, energy will be provided. But if it is a generator, the generator is making the electricity. So you would probably have a resistor. Let me see if I can find. No, it's fine, I can't. You will have a resistor, but this one is a motor. Then 12.1.1, it says here, name the component that ensures that the coil rotates continuously in one direction. It's the split ring, or sometimes it is called the commutator. It's a split ring or the commutator. So to answer 12.1.1, would say it's a split ring, or we can say it is a commutator. And then the second question, let's see, in which direction will the coil rotate? Now, with the motor, remember, we are using the left hand. With the motor, we use the left hand. I have my left hand here. Now, the direction of the current, let's go back here, is from X to Y. The direction of the current is from X to Y. So again, when we use our left hand, in order for the current to be from X to Y, and then our field is pointing like this, that means the force, I'm trying to get my thumb to show here, the force that is acting on the side of XY is downwards. Ne? So if that force is downwards, that means the coil is rotating anti-clockwise. It's anti-clockwise. So the correct answer for 12.1.2 is anti-clockwise. Right. And then we go to the next question. It says here, write down the energy conversion that takes place when the motor is working. If you are looking at your interpretation that you will have written, you will see that you have the energy conversion is from electrical energy to mechanical energy. So it's very important that when you are studying and you are looking at these questions, first deal with the first part of this section, which I would say it's the part where you just put your content into a context. That means simply the understanding of those, whether it's laws, definitions, and everything that has been explained. So the energy conversion here is from electrical to mechanical. Let's see. Another one. All right. Then it goes to the calculations. We will come back to the calculations. I first want us to just look at these beautiful 4 to 5 marks, which we cannot by any chance afford to lose. Let's look at question 13. If you are looking at question 13, it says here in the statement, in the simplified AC generator, the coil is rotated clockwise. So in the statement, it's saying this is a generator. Okay, it's a generator and it's AC. And when you are looking also at this diagram, you say, okay, AC, I'm expecting AC to have slip rings. I want to go back to that summary we did in the first questions so that you can see that once you get into the habit of interpreting questions, you will see that there's actually no new questions that can be asked. It's just that there can be a beautiful rearrangement of words, but the questions themselves will remain the same. Let's see. It's a generator. Okay. You are told it's AC, and you can see on the diagram it's having slip rings. Because it's a generator, it's going to convert mechanical energy to electrical energy. It's going to be based on electromagnetic induction. And then we use Faraday's law. And to determine the direction of the current, we're going to use the right hand rule. Beautiful. So if you get into the habit of interpreting questions, then you are good to go. Let's see. The first question: in which direction does the induced current flow in the coil? Choose from X to Y or from Y to X. Now, if we look here, it's rotating clockwise. That means on this, where's my tool stash? Let's see if I can find something. No. What did I do now? I wanted to. Okay, it's fine. If we are looking at question 13, if you can see here on the arrow, it's rotating clockwise. In order for that to happen, that means the force on this end must be downwards. And then the force on this end must be upwards. And in the question, it's saying you must determine the direction of the current. So if you are using your hand, your magnets, let's just go back again, north and south. So this time you are pointing this way, north and south. And then if you look here, the direction of your current here, let's use our right hand again, will be up, and then you have your finger is pointing like this and your thumb like this, and then you can see that your this middle finger is pointing towards you. That means the current is flowing from Y to X. It's flowing from Y to X. The next question: on which principle or law is the working of a generator based? From your interpretation, you said the working of a generator is based on electromagnetic induction, or you can say Faraday's law. This is the interpretation. So basically what I have written here is the questions that you can expect. There's nothing else. These are the questions that you can expect. Then state the energy conversion that takes place while the generator is in operation. If it's a generator, it will be converting mechanical energy to electrical energy. Now, let's look at this graph. And we say, okay, fine. If we are looking at this graph, can we link the position in which this coil is in with any of the position here on the graph? What we see is that this coil here is in a horizontal position. Therefore, we can link it with the turning points. In maths, I think they call it the turning points. And these turning points are our maximum voltage. This is the maximum voltage or the peak voltage. Then I think also I want to go to question 14, then we will take a break, and then when we come back we will do the calculations. Now, if you are looking at question 14, it says the graph shows the voltage output of a generator. Diagrams A and B show the position of the generator at different times. Now, when you have a generator, there are two possible graphs that you can expect. If it's DC, you are expecting your graph to turn on the upper part only. And if it is AC, then you are expecting a sine graph. Yeah? So this is your interpretation that you are having with you always. Now, when you are looking here at this question, we can see that, okay, this is a sine graph. And then the points where this graph intercepts the time or the x-axis, these are the points whereby my coil is in a vertical position. That means if I have to look between diagram A and diagram B, I can clearly see that in diagram B, my coil is in a vertical position. So the diagram B corresponds with this point, with this point, with this point, and with this point. Then my turning points, this turning point, this turning point, and this turning point are corresponding with diagram A. And let's now go to the questions. The first question is saying, does this generator have split rings or slip rings? It's sine type of graph. It's alternating in direction, therefore it is having what? Slip rings. It's having slip rings. Then 14.2. Which one of the diagrams below, A or B, shows the position of the generator's coil at time 0.10 seconds? 0.10 seconds is a position whereby this graph is intercepting with the x-axis or time axis. This is the position whereby my M or my potential difference or my voltage is 0, right? Therefore, this must be corresponding with diagram B. And then I think you can go through all these questions and you will find that once you have done your interpretation well, then there is no new question that can be asked. So we are going to take a short break, 10 minutes, and then when we come back we are going to look at the calculations. All right. Dumelang hape bagaisho. Now on this part of our session, we are going to take, I think we have around 35 minutes. We will deal with the calculations. Again, for the calculations, I'm going to use your terms and definitions. Basically, here, what I'm really trying to point out to you guys is you must just know how to get to the answer. And the best way for you to get to the answer is for you to be able to interpret the information that is given. Then you will see that everything becomes easy. So for our first question, we're going to look at 13.2. 13.2, we've already dealt with all these other questions that are not calculations. Now, the voltage output for an AC generator is shown below. Here on your graph, I think I've emphasized it over and over again, that at your turning points, that is where you get your peak values. So in this graph, we are having voltage versus time. So our turning points are giving us the maximum voltage. So what we have here is that the peak or the maximum voltage that we are having there is how much? From the graph, we can see that it is 340 volts. It's 340 volts. Then the question says, I think I must close all these other ones which I'm not going to use. Let me see which other one I'm not going to use. I'll close this one as well, so that I only alternate between two screens. So from this question, we can see that the peak voltage that we're given is 340. Then 13.2.1. 13.2.1, the question is saying calculate it says write down the maximum peak output voltage. From your interpretation, you already said that the maximum or your peak voltage is 340. So that means your answer there is 340 volts. And then you get your 1 mark. The second question says a stove is connected to the generator above and delivers an average power. So you are given again here the average power, which is 1,600 watts. That is what is given. Always write what is given. And then from what is given, it says now calculate the RMS voltage. Calculate the RMS voltage. Now from our equations that we are having on the data sheet, in this question we are having a P average, and then we are also having Vmax, we are having Vmax, which is 340 volts. And then the question is saying we have to calculate the RMS voltage. We must calculate VRMS. That is what you must calculate. So when you go to the formula sheet, you must look for a formula which is only giving you one unknown. Let's see. Here we want VRMS. We want VRMS, and we are having Vmax. So this formula would be our easy pick, because we could choose other formulas, but with the information that we are having, always go for the one that isn't straightforward. So from our formula sheet, we are having the formula VRMS equals to Vmax over root 2. So I've chosen the formula VRMS equals to Vmax over root 2. Then you want to calculate VRMS. Usually we discourage learners from, playing around with the formula. Just write the formula as it is, substitute into that formula, and then you simplify. So substitution means where there is Vmax, we write the value of Vmax. So here is Vmax, and the value of Vmax is 340. So where there was Vmax, we are going to write the value of Vmax. Then we have root 2. This 1 mark, you got it from the formula sheet. And then the second mark for your substitution, 340 over root 2. Remember, in order for you to get this first mark, you must at least attempt to substitute into the formula. Then if you take your calculator, let me put my calculator here. We are having 340 over root 2. Then you get 240. Now, when you write your answer, you must always round off to 2 decimal places. So if we are looking at these numbers here, you can see that you keep the 4, but when you look at the next number, it's 1, and the number that follows, you can see it's greater than 5, greater or equal to 5. Therefore, you add a 1 to this one. So we'll have 240,42. (240,42), and then you must write your answer with the SI unit. Then you get your answer of 240,42 volts. Then you get your mark. And then 13.2.3. 13.2.3 says calculate the resistance of the stove. Calculate the resistance of the stove. So 13.2.3, you want to calculate resistance. So from what you have calculated already, the values that you are having, let's see. We are having P average, which is 1,600 watts. We have just calculated RMS, and we found 240.42 volts. From our graph, we read Vmax is equals to 340 volts. So this is the information that we are having, and we want to calculate resistance. So again, you go to your formula sheet. If we look here, we have P, we have VRMS. That means we must first calculate IRMS if we want to use this formula. But when we look at this one, we are having P average, we are having VRMS, and we want to calculate R. So this formula is giving us the physical quantity that we want to calculate, and is only having is having two of the quantities that we are given. So we write there P average equals to V squared RMS over R. It's always nice if you just go for the jugular and speak out straight, and you substitute. You have 1,600. That is your P average. You calculated a VRMS, so it's 240.42, and then from the formula you can see that you must square it, and then you want to calculate R. Therefore your R is equals to 240.42 squared. This is just simplification over 1,600, and then you take your calculator. You have here 240.42 squared divided by 1,600, and then you get here 36.126, and because we have to round off to 2 decimal places, that 2 will become a 3. So our answer is 36.13, and the SI unit for resistance is in ohm. Then you get your mark for the formula, and this was 3 marks, and then you get your mark for the substitution, and then you get your mark for the final answer, which is having the SI unit. So when you're doing a calculation, the most important thing is always write down the given information. Always write down the given information. And then we go now to, let's see, another question. Let's take question, again, question 14 is similar to the one that we just did, I think. We have here your peak. So we have the peak voltage at 312, and then we have what else? We are having resistance. We are having resistance of 40 ohms. So if you, this is question 14, given here is what we're given from the graph. Yes, from the graph we're having V max, and it is 312 volts, and then we are having the resistance of 40 ohms. And then the question says you must calculate the root mean square voltage. Again, you go to your formula sheet. You pick the formula that is giving you the quantity that you want to calculate. If you look here, this is the formula, this is another formula, and this is another formula. So we want to calculate VRMS. Yes, there's VRMS, there's VRMS, there's VRMS. Now, in this formula, there is VRMS, but we don't have the power and we don't have the current. In this formula, there is VRMS, but we don't have the power and we don't have the resistance. But in this one, we are having the maximum voltage. So, go VRMS is equals to Vmax over root 2. Then you go, your VRMS is equals to 312 over root 2. And if you take your calculator, you will have 312 divided by root 2. What did I do now? 312 over root 2, get 220.62 volts. Then the next question is saying a device with a resistance of 40 ohm is connected to this generator. Calculate the power delivered by the generator to this device. You are having already, you are having this value, which is VRMS. You are having 40 ohms. So if you go and you are having the maximum voltage already, you're having this one, and you want to calculate, I think it said must calculate power, the average power. It's very important that you write these subscripts. Yeah, you must write those subscripts, very important. Then if you go back to our formula sheet, we want power, we are having VRMS, and we are having R. Like I said, it's very similar to the previous one that we did. So we will choose our formula, P average over V squared RMS equals to V squared RMS and over R. Then P average is equals to V squared RMS is 220.62 squared over 40. Therefore, you have your answer here, and then your answer squared divided by 40 will give us 1216.8. watts. And yeah, let's see, the maximum current delivered by the generator. So let's see, maximum current. Maximum current is I max. We are having power, we are having resistance, we are having VRMS, and we are having Vmax. So to find the maximum current and the max they are located is, let's see, 4 max. That means for us to find the maximum current, can you see the formula whereby we need to calculate maximum current requires us to have IRMS. That means you can pick this formula to calculate IRMS. You can also pick this formula to calculate IRMS. You can also pick this one because you're having all these values here. So I'm just going to take the first one. P average equals to VRMS times IRMS. And then we have calculated here that P average is 1216.83, and VRMS we also calculated is 220.62. Therefore we have to find IRMS, and if we take 1216.8 and we divide it by 220.62, we get 5, IRMS is equals to 5.52 amperes, right? The question was saying we must calculate Imax. Therefore, we say IRMX is equals to Imax over root 2. And then you say IRMS is 5.52. And then you've got Imax here. You've got root 2. So 5.52 multiplied by root 2, get Imax is 7.80, because if you make this one, you add 1 here, you get 10, and then it adds another 1 here, so it's going to be 7.80 amperes. Now let's try to find another question. The AC generator producing a maximum voltage of 340 volts is connected to a heater of resistance 35 ohm. I think I wanted something where frequency is given, something similar to what we got. But basically these questions, they are nice and straightforward. If you, I think we can do question 4. Question 4.2. If you read in the question, it says a 220 volt AC voltage is supplied from a wall socket to an electric kettle of resistance 40.33. Wall sockets provide RMS voltages and currents. So if it is a 220 volt AC voltage from a wall socket, and we're also told here that the wall socket is providing the RMS voltage. That means this voltage is what? VRMS. Then to calculate the electrical energy that is consumed by the kettle per second. You'll remember that when you calculate the electrical energy, the formulas that you are going to use, I don't think is provided here, but it's if you were going to choose here, we'll take this one. Work done is equals to the square of the current times the resistance and the time. You can also take work done square voltage times the time over the resistance. But you know, most current produces the heat, so there are various options that we can choose. Let's go back. Now time is flying when you are starting to enjoy yourself. We are given here, this is question 4. We are given I think it's VRMS, because we are told that the sockets of the wall provide RMS voltage, and then you're told also that the resistance is 40.33 ohm. And they say calculate the energy consumed by the socket. So your first option would be to calculate, I think if we're having VRMS learning, what we can do is to say, from these many formulas that we are having, we have here time, we have resistance, and we have VRMS. So we can choose this formula. W is equals to, let me just go back to my formula sheet, V squared RMS delta T over R, because we are having resistance and we are having the RMS value. And I think also in the statement they said per second, so the time there is 1 second. There are many options that we can choose, but I'm just going to take one option, 220, and then you multiply by 1, and then you've got 40.33. Therefore, the work done there is 220 squared multiplied by 1 divided by 40.33, and you get 1,200,1. 1,200,1 joules. 1,000 because it's work done, therefore it's in joules. Then the question that follow, calculate the maximum current through the kettle. The maximum current through the kettle. Again, you are having, let's see, on the items that we have, we have resistance, we have voltage, we have time. So is there a formula that we can choose? Let's see, so that we can calculate current, and we want maximum current. So in order to calculate a maximum current, if you look here, if you want to calculate maximum current, you must have the root mean square current. So for us, we are having V RMS, and we are also having resistance. We are having V RMS, and we are also having resistance. Therefore, in order to calculate RMS, and we've also you remember that the rate at which work done also gives us the power. That means our power is also equals to 1,200,1 watts, because it's the time there is 1 second. So power is work done per seconds, I think, coming from this formula. So the power is 1,200. So we are also having power there. That means we can choose, let's say, P average is equals to I RMS V RMS. Then we say we have 1,200,1. We want I RMS, and then we were given 220 volts. Then we've got 1,200,1 divided by 220. You have 5. I RMS is 5,46 amperes. Then to calculate I max, you say I RMS is equals to I max over root 2. Then we've got 5,46 I max over root 2. Therefore I max is equals to 7,71 amperes. Ladies and gentlemen, I have tried my best to do revision for this topic of electrodynamics. I do hope that I have simplified it in a manner that will allow our learners to perform well in this coming examination. I also want to take this opportunity to wish our learners, our candidates, in fact, they are now called candidates, to wish you well, guys. Remember, all of you are having a potential, and the potential that you have, if you place it in the hands of our Almighty God, He will definitely increase it and multiply it and give you the courage that you need, the strength that you need, the focus that you need, the resilience that you need, so that you can pull through this exam. And we pray that any force that might be against you as you are approaching this exam, we just want to take this opportunity and stand against it in the mighty name of our Lord Jesus Christ. We pray that your families will be protected, that you will also be in good health, and that come January, all of us will be smiling. Thank you very much. All the best.